All right, so in the past couple of lectures, we've been talking about how the first and the second derivative can tell us about basically the shape of the graph of a function. And so now we're just going to put all those things together as I entitle, throw everything in a pot. So we're going to put together everything that we've been looking at here recently with applying the derivative to analyze the graphs of functions, and then we'll throw in together the things that we know from pre-calculus about finding symmetries, finding x and y intercepts to the graph, and so on and so forth. So all these things allow us now to really understand the important features of a graph, and that's important when you're modeling and knowing the behavior of the graph in those models as well. And so here I've summarized, similar to what the book has, how the first and second derivatives together tell us about the shape of a graph. And basically, I've got it into, I guess, 7 possible shapes, whereas the book focuses on just 4. But I included the linear shapes over here. And so, first of all, we talk about the first derivative. What's the first derivative tells us? First derivative tells us about when a function's increasing. All right, so across this row, all these graphs are increasing functions, right? Because the derivative is positive. If the second derivative is negative, then the function is decreasing, as in these 3 cases. And then if the first derivative, sorry, I said second derivative, first derivative is less than 0. The first derivative is 0, then we say the function is constant, right? So it's just a horizontal line in that case. Okay, so but the first derivative only tells us some of the information that we need to know, because you can see clearly if a function is increasing, there's actually 3 different shapes that we can think about. And so these shapes now, we talk about the second derivative. And so the book focuses on the second derivative being positive or negative. I'm going to include where the second derivative is 0, where there's no concavity, and that means that the graph is linear. And you can see in this case, right, the function is increasing, but it is linear because the second derivative is 0. Here we have increasing, but since the second derivative is positive, right, it's concave up, which means the derivative is increasing. So the function is increasing at an increasing rate, we might want to say. All right, this is the shape. If the second derivative is less than 0, negative, then the graph is concave down. So now we're increasing, but the slope, the derivative, is getting smaller as we go from left to right. So it's increasing at a decreasing rate. Okay. Now, this little plus plus and plus minus down here is the book's way of denoting these shapes. So the first sign goes with the derivative, right? So the derivative is positive. Second sign goes with the second derivative, which is also positive in this case. Over here, first derivative positive, second derivative negative. So the plus plus shapes look like this, plus minus shapes look like this. I included the plus 0 shape, 0 meaning the second derivative is 0. Down here we have the minus 0 shape, so decreasing but no concavity, so we just have a line, decreasing line. And then minus plus, first derivative negative, decreasing, second derivative positive, concave up. So we're decreasing, but the derivative is increasing as we go from left to right. Right, and it's increasing because, right, if you think about the tangent line as we move from left to right, it's negative at every point, but it's getting what? Less negative. It's getting closer to 0. Okay, so in that sense, the derivative is increasing. And then minus minus, both the first and second derivative being negative, means we're decreasing and concave down. We have this shape. I also include the double O, double O connotation. If both the first and second derivative are 0, then we are just a horizontal line. So basically then, if we can identify these different shapes, the location of that for the graph, we can sort of point and click and drag these shapes to create the graph, if you will. Important then is when we change from from this concave up and increasing concave up, maybe to decreasing concave, increasing concave down rather. So we're going from plus plus to plus minus, or any other transition. We like to talk about those transition points. Those are values of x for which the function will change its basic shape, as summarized in the table above. So where can we change a basic shape? we can change basic shape at local extrema, all right, where the derivative will change from positive to negative or negative to positive. We can also change shape at a point of inflection, right, where we change from concave up to concave down or vice versa. So for example, in this graph here, can we identify the transition points and then the basic shape of the graph for each section? Well, we notice that we have a local maximum right about here. So I'm going to just sort of draw a vertical line showing that, right? So there's a transition point. And where else do we have an extreme value? Down here we have a local min, right? So we're going to go ahead and draw a vertical line at that location. Okay, so there's two transition points, right? But also we said where we change concavity. So do you see where we might change concavity? So here we're concave what? Down. You see the frown. Derivative is decreasing, decreasing, decreasing. But then over here, look here, just a little bit, right? We have what? A little bit of a upward smile, so to speak, concave up, right? The derivative is now increasing through this section here. So somewhere in here we have an inflection point, right? Or a point of inflection. And that's also a transition point. And where else? Well, again, you see it's concave up here, but then what is it here? Concave down, right? So there's another inflection point. And again, another transition point. And then finally, concave down, but then clearly here we're concave up, so somewhere in here there's a transition point. I'm going to assume that there's no portion of this graph that is linear. So, some of you might say, oh, it looks like a line, just a line right here, and that's fine. So you can have a transition to one of my, minus zero portions, right, where the first derivative is negative, decreasing, but the second derivative is zero, and you have a linear section. But I'll just assume that that's not the case here. And so that's also a transition point. Okay. And so these are all transition points. And then using our, again, I'll use this convention, right, that we have with the plus, 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 minus, minus, plus, minus, minus to indicate the shape, right? So the first sign again goes with the first derivative, tells us whether we're increasing or decreasing. Second sign goes with the second derivative, which tells us whether we're concave up or concave down. Again, we're going to assume there's no linear portions in this graph. Okay, so what are we doing here? Increasing, right? So the first derivative is positive, concave down, right? Second derivative negative. Here we're decreasing, right? First derivative negative, concave down, second derivative negative. So plus minus to a minus minus shape. So here's a plus minus, minus minus shape. And then we're still decreasing negative, but notice we're changed to concave up, right? Second derivative positive. Still decreasing negative, back to concave down, minus minus. Still decreasing, first derivative negative, second derivative, what? Concave up now, positive. And finally, we transition what? To increasing again, so first derivative positive, concave up positive. So that's how the shape changes as we move from left to right. And so, basically, when we're looking at analyzing a function from its actual formula, we would want to be able to determine, the sign of what? Both the first and second derivative, and together get these pieces, right? Then we can just sort of connect the dots, so to speak, with the corresponding shape. First, I want to look at a couple examples where we don't give the formula, but where we want to sketch a possible graph. And so we're still going to use the same analysis. We're going to sketch a function that is continuous. I want it to be continuous, so we don't want to have any holes, gaps, jumps, or anything like that. We're going to keep this as simple as possible. And the domain is all real numbers. So remember, it's a function. It must pass the vertical line test. And every vertical line has to intersect the graph. Okay. So what do we have here? We have the first derivative is positive, basically on the interval from minus infinity to 0 for values less than 0. Okay. And the way I'm going to sort of do this is, so the first derivative is positive for values less than 0, but then of course it's what? Its first derivative is negative for values greater than 0. I'm going to do a sign check on the first derivative. I mean, essentially I have it, but I'm going to notice that at 0 we have a transition point. So I'm going to bring this down a little bit. And I want to talk about, first of all, the sign of f prime. Well, I'll come back to that. I'm going to fill in the sign of f prime here, but I want to get all my transition points. So we have one transition point, and then we'll come back and talk about this. But so at 0, we certainly have a change in sign of the first derivative. Okay. Second derivative is positive between -3 and -1, and then 1 to infinity, and then it's negative for values less than -3 and between -1 and 1. Ooh, okay, so what's going on there? So we're negative up to -3, and then we change to positive at -3 in the second derivative. So at -3, that's also a transition point. So I'm going to draw a dashed vertical line for that. So these vertical lines are just for reference here. Okay. And then where else do we have a transition? From -3 to -1, we're positive with the second derivative, and then at -1 we change to being negative. So at -1 we have an inflection point, and hence a transition point. And then finally from -1 to 1, the second derivative is negative, then it changes to being positive at x equal +1. Right. And so what I like to do is to look at the sign of f prime and then the sign of f double prime. Okay, and then together we'll talk about the corresponding shape of f. So we got f prime, f double prime, and then the shape of f. So let's talk about the sign of f prime. So f prime is going to be what? Positive for values less than 0. Okay, so here's x equals 0, so it's positive on this interval, positive on this interval, positive on this interval, right? Between all these transition points, because here's 0, it's less than 0, it's positive. For values greater than 0, it is negative. Okay. What about the sign of the second derivative? The second derivative, first of all, for values less than -3, it is negative. So here's x equal -3, so it's negative. Between -3 and -1, what do we have? It is positive. And then from -1 to +1, -1 to +1, the second derivative is back to being negative, so it's negative here and here. And then for values greater than 1, second derivative is back to being positive. So now we talk about the shape. So what's the shape? So by the sign convention, remember the first derivative sign is plus, the second derivative sign is negative. So plus means increasing, negative means concave down. The shape looks like that. Here, plus plus, increasing, first derivative is positive, so the function is increasing. Second derivative is positive, we're concave up. So increasing, concave up looks like that. Plus minus, right? Back to that shape. Minus minus. So now we're decreasing, concave down. So going down, but we're concave down. and then minus plus, decreasing but concave up. Okay, so there's my pieces, so to speak, of the graph that I want to click into place up here. So what do they all hang on, though? So we've used the information about the first derivative, information about second derivative. Where do we begin? Where do we start this graph? How do I know where to begin with sketching the graph? Well, hopefully everyone notices, right? It's all going to hinge upon this, right? This is the fixed point that we have on the graph. F of 0 is equal to 5. So I can go ahead and plot that point. When I input 0, the output is 5, so I know this point is on the graph. Okay? And now I can just take, basically, you know, like if I had a mouse, I can click and drag this and lock it into place, this little piece, right? So this little piece means, in this interval, we're decreasing and concave down, so it looks something like that. Something like that. And I might need to, you know, of course, stretch it out a little bit, or, you know, distort it a little bit, but it has the same general shape, right? And I just brought it down to here. Again, we have freedom to draw, you know, how steep it drops, but we do want to make sure we're clear on that, showing that concave down shape and decreasing. And then what this shape is, decreasing still, but now concave up, right? So now I'm going to transition to decrease, and I want to make sure I've got that shape like that. And I'm just going to bring it down all the way to the edge, because the domain was all real numbers, right? So I want to make sure that it doesn't stop anywhere. So I mean, I can, you know, draw an arrow. You know, maybe I'm approaching some horizontal asymptote here. I don't know, or maybe it's just going down to minus infinity. Going back this way, right? We're increasing and concave down. And again, I want this to be continuous, so I want to make sure I connect to this point, right? So increasing concave down looks like that, right? Just click and drag that up there. This piece, increasing concave up, that's going to look like that. And then increasing concave down, look like that. Make sure you put some curvature to it. And you can see now that at these points right here, where the second derivative changes sign, we have what? We have points of inflection. And of course, the first derivative test tells us what? We have a sign change from positive to negative, changing from increasing to decreasing. We can clearly see we have a local max here. Okay, so this is just taking the information and sort of hanging, right, using the fixed point that we have, and hanging this shape on that point in constructing the graph. So this is one possible graph that meets the requirements. Let's look at one more real quick. And that's the way I would do it. You know, basically we're going to do the same thing here with the shape of the graph when we're given the formula. We're going to do a sign check on the first derivative, second derivative, and then get the shape. That's exactly what we're going to do. These problems we're going ahead and then sketching the graph given that information. All right, same thing here. The only difference is the domain is everything except for -2. So at -2, I definitely want to have a no point on the graph, right? So it's continuous everywhere else but that point. Now, the first derivative is positive for values less than -2, and negative for values greater than -2. So -2 is a transition point. So I'm going to do what I did last time. Bring it down a little bit low. I like to put my information below the graph. And then second derivative also is positive for values less than -2, and then also from -2 to 0. Okay, that's kind of interesting. Why do they exclude -2? Well, you might recall this domain is everything except -2, so I can't include -2 on there. But then, you know, from -2 to 0, and then for values greater than 0, it changes to being negative. So 0 is also going to be a transition point there. Okay. And in this case, that's all the transition points we have. Right? Transition points we have. So if I come down and I take a look at the sign of g prime, the sign of the derivative, what do we know? For values less than -2, it's positive, so it's going to be positive here. For values greater than -2, it is what? Less than 0, it's negative. Okay. Then we go to the sign of the second derivative. Now the second derivative is positive from negative infinity to -2, and then -2 to 0. So it's positive here and here, -2 to 0. And then for values greater than 0, it's negative again. And so what is the shape of the graph of g? Well, this shape is what? First derivative is positive, second derivative is positive, increasing, concave up. Looks like that. Negative, positive, decreasing, concave up. Decreasing, concave up. Negative, negative, decreasing, concave down. Decreasing, concave down. Okay. Ready to sketch the graph? These are the sections we're going to click and drag into each of these regions. I just need it hanging on something. What do I hang it on? I hang it on the fact that g of 0 is equal to 1. So g of 0 is equal to 1. There's 1 right there. G of 0, right between 0 and 2 for a height. And so let's talk about, what could be happening. The domain is everything except for -2. What could be happening right here to have that? Well, one thing you might think of is we can have a vertical asymptote. Yeah, that'd be good. I can have a vertical asymptote here. And so in that case, this is decreasing concave up. And so as I'm going back towards this vertical asymptote that I'm going to create, then the behaviors we're approaching infinity, right? So we're coming down to that point there, and we're approaching infinity maybe that way. Okay. Then what's happened over here? Well, obviously what has to be happening? We have to be also approaching infinity from the left side. So I'm increasing concave up as well. And then what? Decreasing concave down. So this shape I click and drag and bring it all the way to the edge. Make sure it's clear. It's going to continue to go down for all real numbers here. And there's one possible graph, right? So here I've drawn it so that we have a vertical asymptote of x equal -2. There we have, of course, a point of inflection. Another way we could have drawn this is I could have drawn, instead of vertical asymptote, I could have brought things up to like a hole. I could have a hole in the graph where the graphs approach a hole or something like that. I mean, that's another way it could have been drawn. There's other possibilities, but again, just trying to keep it simple here with this restriction on the domain. So we don't want to have any point at x equal -2. So again, hopefully this is making sense. So I like to ask these type of questions. I have some of them in my non-textbook homework. You want to try those, just given information about the first and second derivative and information to hang it on, so to speak, right? Then we can sketch a possible graph on that information. And I think it's really easy to organize your information by doing these sign checks like I've done down here. And in the next video we'll do the same thing, but we'll work with, instead of sketching the graph, we'll give you the actual formula for the function and then ask you to algebraically determine the sign of the first and second derivative, and hence get the shape that way. So we'll do that in the next video.